Making this video on A2 organic chemistry, a very important chapter in the A2 syllabus. Okay guys, one thing that I would want you guys to know that in the comment section below this video, you may post your questions on this chapter, and as soon as possible I'll try answering them. Okay, so you may post your questions, your topics, whatever queries you have, you may post them and I'll try answering them as soon as possible. Okay, guys, so now organic chemistry in A2. Let's look at the big topics first. Okay, this chapter includes the first topic in this chapter is benzene and its derivatives. Benzene plus the derivatives of benzene. And by the way, this is the longest part of organic chemistry. Then followed by acids and acyl chlorides, acids and their derivatives. Basically, acyl chlorides are the derivatives of acids, acyl chlorides. This is the next topic. Then the third one is the nitrogen containing functional groups of the nitrogen compounds. These include amines, amides, amino acids. Then the next topic is condensation and addition polymers. And then finally the last topic, which is basically a topic from biochemistry, enzymes, the lock and key model of enzymes, the lock and key model of the enzymes. And it's just a brief overview over here. It's not as in detail as in biology. A brief overview of this topic will be given in this chapter. This is entire A-level syllabus on organic chemistry. And let me remind you again that benzene and the derivatives is the basic and the longest part of A2 organic. Okay guys, so now let's get started with benzene. Okay, so what is benzene? Let's start out from its basic molecular formula, which is C6H6. Benzene was first discovered by Michael Faraday. Okay, benzene was first discovered by this scientist Michael Faraday. Well, you don't need to know this for your A levels. And a possible structure of this formula C6H6 was given by Kekulé. The structure that he gave was something like this: a hexagonal ring with three alternating carbon-carbon double bonds. This is one possible form of the same structure, and apart from this, a second possible structure that he gave appeared something like this. The carbons that do have single bonds, they are double bonded in this new structure of Kekulé. Okay, so basically the differences in the two structures are that let me call the carbons over here 1, 2, 3, 4, 5, and 6. Let me give the same numbering here as well: 1, 2, 3, 4, 5, 6. So the difference in between the two structures is that the carbon-carbon double bond, it has actually shifted from in between 1, 2 to in between 1, 6 in this structure. 1, 2, it was in between 1, 2 in the first, let me call this structure A and this structure B. In the first structure, it was in between 1, 2, and in the second is in between 1, 6. The other two bonds have also shifted. This 6, 5 bond has came to 5, 4 in this diagram, and this 4, 3 bond has gone to 3, 2. So these are the two structures that Kekulé gave, and these structures are basically known as the resonance structures or the resonance hybrids of benzene given by Michael Faraday. Resonance structures. So according to the resonance structures, benzene has three alternating carbon-carbon double bonds and three alternating carbon-carbon single bonds. This was the old structure of benzene given by Kekule, but now the recent structure of benzene is drawn like this: a hexagonal ring outside with a circular ring inside, representing both of these resonance hybrids. Basically, it actually represents the carbon-carbon double bonds which are all resonating in among the six carbon atoms. So this resonance ring actually represents the resonating pi electrons in the pi bonds. We'll go on it in a while. We'll talk about the benzene structure in a while, but let me talk about the Kekule structures first in a bit more detail. Okay, Kekule structure, if excuse me, Kekule structure. Okay, now in this structure, we know that there are three double bonds. Three double bonds. Okay, how is a double bond formed? You guys know that double bond requires pi electrons, and it is formed by the sideways overlap of p orbitals. The pi bond, the double bond is formed from one sigma and one pi bond, and this pi bond is formed by the sideways overlap of p orbitals. So if I have p orbitals sticking out of this carbon atom like this, and sticking out of all the six carbon atoms somewhat like this, dumbbell shaped. Okay, so according to Kekule structure, these two might have a double bond, these two might overlap sideways, okay, forming a double bond over here. Then the next two, basically the alternate, meaning the not these but rather the other two, and then leaving the next two and forming a double bond in between the last one. So this is basically the orbital representation of Kekule's first hybrid. Similarly, we can represent the second hybrid of Kekule in a similar manner. Again, a benzene ring with dumbbell shaped orbitals sticking out of the hexagonal ring, and then these two, the alternate, which were not overlapping in the first diagram, overlap, and then the next two which were not overlapping overlap, and then the last two which were not overlapping overlap sideways to form the double bonds in benzene ring. These are the two resonance hybrids given by Kekule. Okay, so basically what happened was that the Kekule suggested a ring structure of benzene with alternating carbon-carbon double bonds and carbon-carbon single bonds. This structure, as we can see over here, is unsaturated because of the presence of double bonds. Kekule structure is unsaturated because of the presence of the double bonds in the pi electrons. Now let's compare this structure to alkenes. We know that alkenes also have carbon-carbon double bonds and are unsaturated. Alkenes, benzene, and the reagent with which we are going to test them. Okay, now something very interesting happened when this benzene was tested with the reagents that are usually tested, which are usually used to test for alkenes. The first reagent that we can use is bromine water test, the very basic test for alkenes with aqueous bromine. What happens that in with alkenes, the bromine water, it gets decolorized. Colorized. Okay, the second test that we can perform on alkenes is using cold dilute KMnO4, cold and dilute potassium manganate 7, KMnO4. What happens with alkenes is that this cold KMnO4, which is initially purple in color, changes color from purple to colorless. With alkenes, there is a third test as well that we can do on alkenes, which is basically hydrogenation, that requires hydrogen gas plus the platinum catalyst at 25 degrees Celsius and 1 atmospheric pressure. What happens is that this hydrogen and the platinum catalyst, they hydrogenate the alkenes and convert them to alkanes. Alkenes are converted to alkanes, so they basically rapidly react with alkenes at a temperature of 25 degrees Celsius and 1 atmospheric pressure. Reaction occurs. So basically this is the room temperature, the standard temperature and pressure at which the reaction occurs. With benzene, something very interesting happens. When we react benzene with either the bromine water test, when we test benzene with the bromine water test, or the cold KMnO4, in both the cases, no reaction occurs with benzene. Benzene gives no reaction at all. Although it's an alkene and according to CAIE structure it is unsaturated, it should give positive tests for both these reagents, but it does not. And as far as the hydrogenation is concerned, no reaction occurs until it is heated to 100 degrees Celsius and 100 atmospheric pressure temperature is applied. Basically temperature and pressure being very high temperature and very high pressure is required for benzene to react with hydrogen and platinum catalyst. What does this suggest? This actually suggests that bromine water or the cold KMnO4, they can rapidly react with alkenes. This means that benzene, but do not react with benzene. This actually means that benzene is more stable as benzene. Benzene's own structure is very stable. It wants to stay in the C6H6 form and does not want to change. So that's why very harsh condition of 100 degrees Celsius and 100 atmospheric pressure is only enough to convert benzene to some alkane. Basically, when benzene will get hydrogenated and in presence of platinum catalyst, hydrogenated in presence of platinum catalyst at 100 degrees Celsius and 100 atmospheric pressure, it will get converted to cyclohexane because hydrogenation occurs and all the hydrogen, all the carbon-carbon double bonds are hydrogenated and converted into an alkane, a cycloalkane, which is cyclohexane. So these reactions, these basically suggest the very high stability of benzene. Benzene wants to stay as benzene and does not react easily with any of these reagents, and it reacts at very high temperature and high pressure with platinum and hydrogen gas. Now let's talk about the new structure of benzene that I recently made. Okay, this new structure of benzene has a hexagonal ring representing the 6 carbon atoms and a circular ring inside representing a donut shaped electron density inside of benzene, which is above the hexagonal and below the hexagonal ring, above and below the hexagonal ring. What happens is that in this structure it is suggested that the 6p orbitals of benzene, each carbon atom has a p orbital sticking out of the benzene ring perpendicular to it, right? As we made them earlier. And according to CAIE structure, any two carbon atoms which are alternative to each other, they overlap sideways and form double bonds. But according to the new structure, it is suggested that all the orbitals of benzene, they overlap equally with each other, forming a donut-shaped electron density above and a donut-shaped electron density below the benzene ring. So basically the p orbital of each carbon atom, it equally overlaps with both the neighbors. The p orbitals of this carbon also overlaps equally with both the neighbors, and hence as an entire electron density above and below the benzene ring is made, which is donut shaped. This electron density is very important. It is the basic property of it is the basic that gives benzene its basic properties. This is the major reason why benzene is different from all the alkenes. This is the reason why benzene is very stable. So the reason for the high stability of benzene is its electron density above and below the benzene ring. This electron density is given a special name. It is basically, since these electrons, these are actually the pi electrons which are continuously resonating above and below the benzene ring. They are not stationary, but they are continuously moving above and below the ring. So they are basically delocalized pi electrons. And these delocalized pi electrons of benzene, they are both above and below the benzene ring, above and below the benzene ring. And these delocalized pi electrons can give extra stability to benzene, due to which it is very inert towards both the bromine water test and the KMNO4 test, which is usually reactive or positive with all the other alkenes, with all the alkenes actually. Okay, now let's compare the bond lengths. Oh, one more thing on the structure of benzene. This is actually the best structure that is known yet. Okay, Kekule's structure was not as good enough as this structure. So that's why in most of the places you see benzene will be made like this, drawn like this. Okay, now let's compare the bond lengths of carbon-carbon. Okay, the carbon-carbon single bond has a bond length of 0.154. Okay, these bond lengths, nanometer. Over here, the bond lengths are given in nanometer, and these are actually the type of bonds. Okay, I'm writing the type of bonds over here, and the bond length in nanometer on the other side. Type of bond and bond length in nanometer. Okay, carbon-carbon single bond is 0.154 meter in an alkane. Okay, carbon-carbon bond in benzene. The carbon-carbon bond in benzene is 0.14. Carbon-carbon bond in benzene is 0.14 nanometer, and the carbon-carbon double bond in alkenes, in normal alkenes, is 0.134 nanometer. Now, from this trend, what do we observe? The carbon-carbon single bond is the longest bond, and the carbon-carbon double bond, obviously because the bonds have doubled, so the nuclear attraction in between the two bonded nuclei will increase, and the electron density in between. The nuclear attraction between the bonded nucleus and the electron density in between will increase, and so the bond length will shrink and will decrease. So this is basically a bit background from the AS chemistry. Increase the double bonds or the triple bonds have shorter bond lengths as compared to the single bonds. Okay, so now as the bond becomes double, its bond length has decreased. In case of benzene has a bond length that is intermediate in between both the bonds, the double bond and the single bond. It is 0.14 nanometer, which means that benzene is not the structure that was suggested by Kekule. It does not have double bonds, it does not have only single bonds, but rather, and one more interesting fact about benzene is that all the carbon-carbon bonds in the benzene ring have equal lengths. All bonds have equal lengths, and these lengths are equal to 0.14 nanometer. So since in benzene, all the carbons in benzene, they are equal in length. Since they are equal in length, so the structure of calculi is not a very valid or a very good structure to represent benzene, because experimentally its bond length is 0.14 nanometer, which is in between both the single and the double bond. So it's basically a partial double bond character that benzene has due to the delocalized, and this is also due to the delocalized pi electrons that I just discussed earlier. Delocalized pi electron density above and below the benzene ring, because it keeps on resonating above all the 6 carbon atoms in benzene. Okay, so this was an important point that we covered. Now to cover it up, to sum it up, in benzene all the 6 orbitals they overlap equally. We discussed that earlier, that the takeaway point is that all orbitals in benzene, they overlap equally with each other, making all the bond lengths equal. All the carbon-carbon bond lengths are equal and have a partial double bond character. This is the first, and they have a partial double bond character. Okay, then the next point is, due to this overlap of p orbitals, a donut-shaped electron density is made above and below the benzene ring. This is also due to the equal overlap of all the p orbitals or the pi orbitals of benzene. The pi electrons are delocalized over the entire ring, which makes all the bond lengths equal. We've discussed that as well. Now the last point, and a very important point on the structure of benzene, is that all these carbon atoms, okay, this is our benzene over here, and if I number the carbons, 1, 2, 3, 4, 5, and 6, all the carbon atoms, their hybridization is sp2 hybridized. All the carbon atoms are sp2 hybridized. And the bond angles in benzene. Which bond angles am I talking about? This one, the carbon-carbon bond angle. Carbon-carbon and the hydrogen, which is basically attached to each of the carbon atoms in benzene. This bond angles, this bond angle, this bond angle, all the bond angles are equal, and they are equal to 120 degrees. So 120 degrees bond angle mean that their shape will be trigonal planar. So carbon atoms are sp2 hybridized. The bond angle, the carbon-carbon-carbon or the carbon-carbon hydrogen, carbon-carbon-carbon, this angle, or the carbon-carbon hydrogen, even this angle is how much? It's equal to 120 degrees, due to which its shape is known as trigonal planar. On the structure of benzene. So this is an important video on benzene. The resonance structures are important, and this table is important. And what else? Yeah, the electron density and the delocalization of pi electrons is also very important. And these bond angles, okay, bond lengths actually. I've seen exam papers uh, exam questions on these. Okay, so better learn this. I mean, they never ask you the values, but they do ask you the reason why the benzene has an intermediate value in between the carbon-carbon single bond and the carbon-carbon double bond. So you better be able to explain it to them in terms of the delocalized pi electron density, the bond's length being equal. Okay, so basically what you need to do is that to answer that question, there are mainly 3 points that you need to keep in mind, and you need to write your answer along these lines. Okay, the first point is that all the p orbitals of benzene, they overlap equally with each other, overlap equally with each other or with each of their neighbors. Okay, the second point is due to which there due to which a delocalized all the electron density, or basically no, to make it even better, the pi electrons become delocalized. This word is important. Okay, delocalized pi electrons is the key word of this answer. The pi electrons become delocalized. Delocalized pi electrons, due to which the bond lengths become equal. So p orbitals, they overlap equally with each other. The pi electrons become delocalized, and yeah, delocalized pi, and they resonate. But the third point, it's better to write it if the question is for 3 marks, but if it's just a 2-mark question, so the first 2 points are enough. The pi electrons, they resonate above the benzene ring, above and below, and below the benzene ring, making all the carbon-carbon bond lengths equal. And one additional point that you may give is that due to this, the carbon-carbon bonds in benzene get a partial double bond character. Partial double bond character. Okay guys, so that's it on the structure of benzene and on the resonance hybrids of benzene. Yeah, these values are also important of bond angles, the shape of carbon atoms, the shape of benzene actually, it's triple planar, and the hybridization of carbon atoms is also important. So, and yeah, the word stability, the stability of benzene actually is also very important. So better also remember that the reason for stability are the pi electrons themselves, the delocalized pi electron density above and below the benzene ring. Okay, so thank you so much. Meet you guys in the next video on benzene, in which I'm gonna discuss the stability of benzene in a bit more detail, and it's even more important.